Hey there, and welcome back to another PCG tutorial. Today we'll continue exploring the wonderful world of GPU generation. In the last episode, we had a lengthy introduction to GPU generation with PCG, showing how we can push high-density foliage on the landscape. In this episode, we'll continue to see the different ways of scattering and filtering points, using texture and landscape grass layers. I also want to show how to bypass a very big limitation of GPU generation, which is the no collision issue. Spawning lots of trees without collision is often non-suitable. I'll build up on all I did in the previous episode, so you'll probably want to familiarize yourself with the concept I introduced before. As usual, the project files are available on my GitHub, and you can join the Unreal Source Discord server if you have any questions. Without further ado, let's dive right into it. I'll start with a new open world map, where I'll place a PCG volume that will be covering the full landscape. On the PCG component, I enable generate at runtime and check is partition. And on the PCG world actor, I'll check treat editor viewport as generation source. I also make sure that the landscape cache is set up as serialized only on cook, so we can have landscape data while playing in Pi or package mode. For the little explanation on why we have this option to never serialize by default now, it's because if you do no PCG at runtime, you don't have to serialize the landscape, as you won't need it. And the serialization can increase the final package size. And we prefer to avoid having unexpected package size bump, so if you have any issue with PCG not generating in Pi runtime, check the logs and check that the landscape cache is marked as serialized. First thing we want to do is to define our texture we're going to sample. If you played a bit with PCG biomes, you might have seen a texture with a lot of bright colors that defines the biome. We're going to do the same for our map. I already have a very simple 1024 by 1024 texture painted with 3 colors, pure red, pure blue, and pure green. They will define 3 biomes. Let's start with a very simple example where I'm going to sample my texture and spawn trees only where it's blue. First thing, we want to scatter points on the landscape, so we're going to reuse what we've done in previous episode. So I'm going to copy the HLSL code we did in previous episode and adapt it a bit so it's better suited for us. So I'll copy it in my folder and name it texture landscape scattering. Let's recap what this code does. The first thing is to create a 2D grid for our cell. If you remember last episode, we do not have an array here, but just a single point. Since this code is executed for each point, we have a different point at each execution, that is given by element index. We then pull all landscape bounds to avoid spawning outside of the landscape. We have a constant for displacement. Since we do not want to have our trees placed on the grid, we want to jitter the points. For any random process, we need a seed, so we compute the seed using the node seed with getSeed, and the future point seed based on its position with compute seed from position. We then generate a random displacement and apply it to the position. Then we want to make sure to discard any points outside of the landscape. I discovered that there is an even more compact way of defining the condition using any. With HLSL, the less than will be applied per component and generate a Boolean vector. Any will return true if any of those bool are true, which make the condition way nicer. Make sure to only compare X and Y component. If the condition is true, it means we are outside of the bounds, so we discard the point and immediately return. Then we do the projection on the landscape using the getHeight function and store it into the Z component of our position. We also do a random scaling. We compute the normal and generate a quaternion out of it. Same for a random rotation around Z. We multiply the quaternion together to get the final rotation and write all our values into the point. First, I want to have more control on what the HLSL code is generating. I'm going to rename my landscape bounds bin by paramsbin. This will contain all the parameters that will influence the generation. On top of boundsmins and boundsmax of the landscape, I want to have a vector2 to control the random scale that is applied to the generated point. and I want to have an option to follow the normal. For foliage, it makes sense that it follows the normal of the landscape, but for trees, it is a bit weird. So we want the trees to stand straight. So we'll have a bool for following the normal. And it will be the quaternion identity in place of the normal rotation if it is not following the normal. For the graph setup, it'll be the same as last time. We start with the graph settings, enabling hierarchical generation with an unbounded grid size as default. We want to get the landscape using the getLandscapeData. Then we need to prepare our params. So we'll do a getBounds on the landscape data to get the landscape bounds, and have two more constants. A scale, that is a vector 2, set it between 0.5 and 1, and another one, FollowNormal, that is bool. I set it to false. We add all the attributes together. I'll then create a point generator node, and I need to set up the pins. The first pin will be the landscape of type landscape. It needs to match the name in the HLSL code, and also a param input pin of type attribute set. I want to place the tree on a 512 mm grid, so I add a change grid size node and plug the landscape in it, and then plug everything into the HLSL node. I set the kernel override with the code I just presented, and I got an error because the output pin is not named correctly. It is expecting to be out points, so I'll just rename it. If I enable the debug, we can see we have our points. I increase the number of instances to see it better. They are randomly scaled and rotated, while not following the landscape normal. So far so good. We went back to the previous episode results. Now that we have our points, let's see how we can use the texture to mask points. We'll create a new node that will be a point processor. We want to process the input points. We're going to add a new pin, that is a texture pin. In this texture pin, we plug a getTextureData. Since the texture is going to be used on the GPU node, it means that we don't need to read it on the CPU, so we can enable skip readback on CPU. Then we will set up our texture and plug the getTextureData node into the texture pin. We are now ready to sample it. First, we want to get the position of our point. So we'll use inGetPosition using the nDataIndex and the element index and storing it into a position variable. Then we want to sample the texture. If you check the declaration panel, you can see that under texture, we have a lot of functions. The one that interests us is the sample world position. So we're going to sample the color at the position of the point. So we're going to create a float4 variable, and we're going to use the texture sample world position. The data index will be 0 because we just have a single texture, and the position will be the position of our point. This will stretch the texture to match the original PCG component bounds and transform the world position into UV space for the sampling. As a first experiment, we want to discard points that are not on the blue mask. The condition is pretty simple. If color.b is less than 0.5, discard the point. Same as before, out remove points plus a return statement. If it is on the blue mask, we want to forward our point. There is a macro for that. To find it, open the PCG_CS_shader utils file. In this file, you'll find the PCG copy all attributes to output. This will copy everything from the input points into the output point. We need to define the target pin, the source pin, the target data index, the target element index, the source data index, and the element index. back in our custom node, removing the kernel override, the target pin is out, the source pin is in, the target data index is out data index, the target element index is element index, the source data index is in data index, and the source element index is element index. Since it is a 1-for-1 processing, the target and source element index are the same. If I inspect the node, you can see that the points are correctly generated. Now, if I debug this result and change the scale method to absolute to see the points, you can see that I only have points on the blue mask. Everything outside is cold. Though the cut is a bit too harsh. Maybe having some kind of blending between no points and points will be nice. We can have that by introducing a bit of jitter when sampling a texture. Instead of sampling at the point position, we sample the texture slightly offset from this position. Let's go back to our HLSL node and add some randomness. I'll copy the line from the previous code to compute the seed. But instead of computing the seed from the position, we'll take the point seed. In the previous node, we write our seed into the point, so this value will be set and different for all points. To get the seed, it's the same as all the other point properties in getSeed, with the same parameter than the position. Then I will replace the compute seed from position using this new point seed. We'll then have a blending parameter. I'll hardcode it for now with a value of 1000, meaning that we'll sample the texture in a radius of 10 meters. I'll remove the const qualifier on my position, since I'm going to modify it, and we'll do the same thing as the previous node, and we'll do a lerp between minus blending and plus blending using a random number. We change the position using this offset and use that one as our sampler. Now you can see that the cut is less visible. I can even push the blending to 10,000 for an even more blending range. This is all very interesting, but just masking points is not what we want here. We want to spawn stuff depending on the color of the texture. For that, we're going to take the data set approach that was presented in 5.4 new feature episode 2. I'll go quickly on the setup as it's exactly the same. I will create a new structure and name it mesh info. This structure will hold the mesh, the scale, and the color. I'll then create a new blueprint class of type primary dataset. And have an array of my structure, making sure that variable is visible. And finally, I create a new dataset of my new class. In this one, I'll set up 3 entries, each with a different mesh tree and the color associated using the red, blue, and green, and a scale of 1 to start. To control the blending factor, I'm going to add it to the dataset as a float. And setting the default value to 1000. Now that we have this dataset, we'll pull the data into PCG. We'll create a new graph parameter of type mesh asset, initialize it with the data asset I just created, name it forest, and drag the parameter into the graph. From there, we want to extract the values, so we're going to use get property from object path. If the property name is none, it's going to extract everything from the structure, but you can see that we only see the blending factor here. If you remember in previous episode, we said that the arrays are not pulled directly, so we need to have another node to pull the meshes directly. and we add them all together at the end. And we can see that we have all our parameters, even all the meshes, all the colors, and all the blending factors. By the way, new feature, if you Ctrl+click on a path, it will jump to the asset directly from the attribute table. Pretty neat. Now we need our point processor to read those params. To do so, we're going to add a new input pin named params of type attribute set. Our goal here is to assign a mesh to each point depending on its sampled color. For GPU nodes, we need an extra step. The node needs to know all the new attributes on the output data with their type. This is set up on the output pin under GPU properties. In our case, we want to have a new attribute named mesh of type string key. It's important to note that HLSL doesn't have a native string type, like a mesh path. So strings are mapped as keys, and they can only be copied from a string that exists in the input pin. You cannot set the string directly in HLSL. Now that the blending factor is a parameter, we're going to pull it from the params pin. And you can see that the refresh is dynamic. I can change it, like put 10,000 for example, and you can see that the blending is automatically updating. We now need to select which asset to spawn depending on our color. We can remove the part that removes the point, since we'll keep them all. We will select the asset that has its color the closest to its sample color. For that, we need to keep the info on the selected asset with uint index equals 0, and a minimum distance, that is a float, that is set to an enormous value as an initial value. We need to loop on all the values from params and compare the color with sample color. To know how many values we have on the params pin, we can use the params getNumElements. We create a for loop between 0 and the number of element, incrementing I by 1 at every loop iteration. For each element, we pull the asset color into a float for. The data index is 0, because we just have a single data as input, but the element index is not 0, it's I. It's the ith element in the params, and the attribute is nameColor. We then compute a difference vector by subtracting the asset color by the sample color, keeping only the RGB components. We do a dot product of the difference with itself, which gives us the squared length of the difference. If this value is smaller than our current mean distance, we make it our current mean distance, and index becomes I. Before spawning our mesh, we'll debug our selected index to see if it is the right color. We're going to set the output color using our selected index and the asset color. Then we'll plug it into a debug node, set the scale method to absolute and the scale of 5 to see something, and set the material override to color. And we can see our texture with the nice blending at the boundaries. We can even change the blending factor to 10,000 for an even more intense blending. Now we can pull the scale and the mesh. The scale is a float, with the element index being our selected index. And the mesh is a uint, since is the key, and we use the param set getStringKey to get the key. we set the scale on the output point to be the input point scale times the asset scale, and we set the string key on the output point. And we can see that our mesh is set up correctly. We can then plug our point processor into a static mesh spawner, use the mesh selector by attribute using the attribute mesh, and make it run on the GPU. And we have our trees following the biome that we defined. They're a bit small, so let's make them a bit bigger. It's a bit too dense, so we're going to reduce the number of points it is generated. One caveat as stated at the beginning of the video is that those trees has no collision. That's because any mesh they spawn on the GPU doesn't have any CPU information and so no collision. To counter that, we can spawn the same mesh invisible on the CPU on a very small grid to be very cheap on the resources. For that, we're going to use the results of the static mesh spawner, make it into a very small grid, like 800 for example. Keep only the points at the grid level with a call points outside actor bonds, and do a static mesh spawner by attribute again, but this time on the CPU. We make sure to have a collision preset to block all and make visible to false. If I go back in Pi, you can see that now I have collisions on the trees that are close to me. Alright, in this video we saw how to sample a texture asset on the GPU for biome placement using data asset, and also add collision on top of that. This video is already long enough, so I'm going to cut it in two and release the next one where we'll talk about landscape grass. But I cannot leave you without a little teaser. Wonderful grass. I hope this video was useful, and I'll see you in the next one. In the meantime, have fun with the plugin. Take care.